Okay, North Central, this is the guy who's supposed to be responsible for you, and apparently he needed to get something out of his locker. Great, so now here we go. Whoop. Please, he didn't do his homework. He had to beat somebody up for it. All right, so yesterday we started talking about this idea of relative magnitude. Let me write it over here for the North Central friends. When I say relative magnitude, really it's just a conversation of I am comparing two functions. I am comparing specifically the end behavior of two functions to figure out which one grows fastest. And the way that we determine which one grows fastest is we do this limit as x approaches infinity of f of x over g of x. We take the ratio of the two functions, we take the limit as x approaches infinity, and then depending on the answer, like if the limit is 0, what is the conclusion? You take the ratio of these two functions, the limit as x approaches infinity of the ratio comes out to be 0. What I care about is not the number, but what does the number tell you about the functions? And feel free to use the notes if you need to. Celeste, what's the conclusion here?
That g of x grows faster than
This means that g of x, excellent, g of x grows faster than f of x. Okay? Now, another option is that you could be doing limit as x approaches infinity of f of x over g of x, and you get infinity. What is the conclusion there? You're frozen for a little bit. If you take the limit as x approaches infinity of the same two functions, the same ratio, you get infinity. Carmen, what's the conclusion?
that f of x grows faster than
F of x grows faster than f of x.
g of x.
Yep, f of x grows faster than itself. Makes no sense. No sense. We're okay? We get the two options? There's one more option. Aaron.
If it comes out to be a finite number,
Okay, but let's be specific. Not it comes out, but the limit.
the limit of f of x over g of x.
Limit of f of x over g of x. If that comes out to be, I think we called it L.
Yes.
The importance of L is that it is a finite number. Okay, so some finite number. Aaron, what's the conclusion?
That they grow at the same rate as x approaches infinity.
F of x and g of x grow at the same rate. At the same rate. All right. Cool. Honestly, those are just some like limit facts that you need to get into the brain, and hopefully not too bad. Okay, my flashcard people, maybe you want to turn this into a flashcard, highlight it in the packet, that's fine. So yesterday we went through and you guys like did this comparison of like 10 different functions, and there was a conclusion here. There was one that grew slowest of them all. Which one grew slowest? Natural log. Some folks call that the slog function because it just slowly grows. So that natural log function was the slowest growing function of all the functions that we saw. Now, and I drew it a little bit badly there. It's a little bit exaggerated. The log function does grow. It grows forever. It doesn't have a horizontal asymptote, but it grows really slowly. Everybody good? Mm-hmm. Slowest growing function is the log function. After that, you hit the land of the polynomials. And what did we discover in the land of the polynomials? What did you already know in the land of the polynomials? How do you decide which one grows faster in the world of polynomials? We look at the degrees. The bigger the degree, the faster it grows. And the fastest growing functions that we saw yesterday was in the far end of that spectrum. We had the log was like slowest, and then we had like polynomials. And then there was like a branch of functions that we looked at. We had the log function, we had the polynomials, and then after that, the fastest growing functions that we looked at yesterday. E to the power of 3x grew really fast, 3 to the x grew fast, e to the x grew fast. As a family of functions, we refer to them as the exponentials. So log function grows slowest of all, followed by polynomials, followed by the exponentials. In the world of polynomials, what I'm going to say is look at the degree. And the bigger the degree is, right, the bigger the degree is the bigger your degree is, the faster the polynomial grows. In the world of the exponentials, what I'm going to say is look at the base. Is everybody mostly okay with this idea? Okay, so I'm going to give you guys 1 minute to do one question. Friends at North Central and other places, feel free to try this one on your own. On page 38, this question came off the 2013 AP exam. It was question number 12, calculator inactive. I'm curious to see what you can do completely on your own in 1 minute while I take attendance. 5, 7, 9, 11. Use your notes if you need to. All right, friends, we're ready to lock it in? Give an answer? How many of you guys are going to go with A? Oh, David, can you turn that off? Okay, B. C. D. E. Okay, that was really scary because I forgot which answer it was. I was like, oh my God, they don't know anything at all. Okay, if I were to take the limit of f of natural log of x over x to the 99th power, what's going to happen there? We're going to approach 0 because the natural log grows really, really slowly. X to the 99th is a polynomial, grows faster. So here you're going to get 0, I agree. 1 works. Over here, if I take this limit, e to the x over natural log of x, you're going to approach infinity. Maybe you would say limit doesn't exist because of unbounded behavior. But in the world of relative growth, relative magnitude, we're going to say e to the x grows faster. We're heading to infinity, not this one. And then this last one, x to the 99th over e to the x. That should work as well. So 1 and 3. Honestly, one more time. How many guys got that one right? Okay, I got to tell you, it was a really scary experience for me because I forgot the answer was e. And I was like, oh, I thought I did a good job. I thought they were really smart. Clearly, you were all way smart. David, the verdict's still out. Okay. All right. So, awkward transition here. Very, very awkward transition. We have 22 minutes to do what I would normally do with friends in a whole 55-minute class period. I don't want to go so fast that I break anybody in the process, but the good news is, Giselle, and you're like, oh, it's going to be bad. Okay, the good news is you already know a lot about this topic. The topic is continuity. Okay? Continuity. What do we know about a continuous function? I say continuous function. I bet a bunch of parent functions come to mind. For example, let's get some hands. Continuous parent functions. Give me one and you're frozen. Y equals x squared is an example of a continuous parent function. Others. Aaron, then you're frozen.
I mean, wait. I was just going to say y equals x.
Wait, one more time?
I was just going to say the base one.
The base one, which is?
Y equals x.
Y equals x is a continuous parent function. Y equals x squared is a continuous parent function. Before somebody says y equals x cubed. Yeah, I know that one too. All right, so let's take all polynomials off the table. All polynomials are continuous. David, give me another one.
Y equals the absolute value of x.
Y equals the absolute value of x. Love it. Stephen, give me another one.
Y equals the square root of x.
Y equals the square root of x. Love it. Andrew. Natural log of x, continuous. North Central. No, too bad. Friends over here.
Give them some options.
Continuous parent functions. Palamon.
Sine of x.
Sine of x. Friends over here. Cosine of x. One more and I'll take the focus off of you. Sure, sine of x is still continuous. It was continuous a few seconds ago. It's still continuous. Everybody okay? I want now parent functions that are not continuous. Parent functions that are not continuous. David.
1 over x squared.
1 over x squared. Love it. Get in while the getting's good. 1 over x. Other ones. Discontinuous parent functions. Tangent of x. 1 over x squared plus 1. Minus 1. 1 over x squared plus 1 makes that hill shape. That is continuous.
Right there.
Yeah.
No, it's right there. That's what I'm saying.
It's also right there. Way to rat her out, Aaron. Okay.
What?
Okay. We're good? We're good. All right, so now let's get really good at this. I want you guys up on your feet for this. Yep, everybody's up on their feet. All right, here we go. More power teaching. Stephen, maybe you want to move the camera so that the friends at North Central can join us as well, and they can see everybody doing this. Well done. And if you're managing the camera, they're not going to see you do it. So like, yay for you, but can you scoot over a little? Sorry, I'm not like bullying you. But okay. All right, so here's the thing that you know. In order for a function to be continuous, let's do that please. In order for a function to be continuous, there can be no holes, no jumps, no breaks, and no, favorite one of all, vertical asymptotes. All right, the hole is considered a removable discontinuity, so cover your hole. Don't think about that too much. All right, so one more time, we're all gonna do this together. The words are up here on the screen. Okay, Stephen's doing it back there. Here we go. 1, 2, 3. In order for a function to be continuous, there can be no holes, no jumps, no breaks, and no vertical asymptotes. A hole is considered
Removable discontinuity.
We're good?
Yes.
Does this match everything? Don't sit down yet. You can't be that tired. Okay. Does this match everything that everybody already knows about continuity?
See.
Right? If I gave you a graph, you'd look at it and be like, clearly continuous, clearly not continuous, we're good. All right, now you might be having some flashbacks to last year in pre-calculus. You guys started looking at like continuity at a point. Like sometimes they'd give you the graph. If they give you the graph, it's easy. But there was this process that you went through, this 3-step process to show a function was continuous at a point. And you have to show all 3 steps. When I say a function is continuous at a point, I mean 3 things. Number 1, the function is defined. There is a point there. Number 2, the limit has to exist. Why am I doing this?
Because of
Limit from the left and the limit from the right have to be equal to each other. Now here's the thing, what I've said so far, the function has to be defined, so there has to be a point there, and the limit has to exist. Those 2 things alone are not good enough, because the third thing is you need, however the function is defined, to be exactly equal to what the limit is. Why? Why do you need that third piece? We've said the function has to be defined. We've said the limit has to exist. Isn't that enough for continuity? Can you think of what the graph might look like? You have a function is defined and the limit exists, but it's still not continuous. Talk to somebody near you.
Because it will be approaching there and then
Like it could reach.
it could be like the orange jumps can, but it could be different.
Okay. So the conversation seems to be something around the lines of like, there could be a hole in the graph.
Yes.
Okay. Now, could the limit exist and you have a hole?
Yes.
Absolutely. Is the function defined at a hole?
No.
No. So could it be possible to have a limit that exists and the function is defined and not continuous? Okay. Could the limit exist, and you guys said there's a hole,
Oh, yeah.
and the function is defined, but you're still not continuous?
Yeah. That's possible. because
Where?
we're-
I'm going to need another hand, I think.
Wait.
Here's the hole.
Yes.
How do you define the function? Now you, oh, it's very nice. But in that case, if you just covered up the hole, is the function continuous? Yes. I'm looking for why that third statement has to be there. Right? The first statement says function is defined. Second says limit exists. You need the third piece because what if you've got the hole and you've got the function defined up here? Would you guys consider that to be continuous?
No.
No, it's a jump discontinuity.
You'd have a jump discontinuity. Well said. Stephen, you're doing a great job there. Okay, I need you guys for one more time. So here's the power teaching moves. Okay, proving continuity at a point. In order for a function to be continuous at a point, the function has to satisfy three conditions. Number one, the function f of c is defined. Okay, so like make a fist. Number two, the limit as x approaches c exists. We're okay with that? Okay, number three, the limit as x approaches c is equal to f of c. I want to make sure that it's not a hole, we're closing the hole. Yeah, don't hit snooze, turn it off.
Wait, how?
Slide it.
Oh.
See, I don't know about iPhone.
Welcome to the 21st century. All right, so one more time. We're going to go through this on the count of three. Let me get over here in my big sweaty self. You guys have the words up there. Hi, North Central. On the count of three. In 1, 2, 3. In order for a function to be continuous at a point, the function must satisfy three conditions. Number one, f of c is defined. So show me that point. Show me that the function is defined there. You're like punching the airbag. Number two. That means you're going to have to be checking limits. You're going to have to check a limit from the left and check a limit from the right. Number three.
Limit of f of x as x approaches c equals f of c.
Equals c. Okay, you need the limit as x approaches c to be equal to f of c. You cannot have a hole. You're going to have to check all three things, okay? If the function fails even one of these conditions, the function is said to be discontinuous at x equals c. Done. F c. All right. So, if you need to transfer that stuff into your notes, it's at the bottom of page 39. Right, there's a little box there. I know. Okay, so make sure you get all three conditions. When we talk about continuity, I need to see all three.
First was in the box, said the third one, and I was like,
Thank you for holding me to a ridiculously high expectation. The first year I did this continuity at a point, I did it so fast, I jammed my thumb into my eye. I was going way fast. I jammed my thumb into my eye, pushed my eye back, and collapsed on the floor. It was bad. But man, did they remember those three conditions.
Is that when you taught Janet and Arthur?
Possibly. It's all a blur now. Really, it's all a blur. Yeah, I got moves. All right. Everybody good? Good. All right. So we're going fast here. All right. What I want to know is each of these three functions up here. I would assume you can all look at and say, clearly this function is not continuous, right?
Yeah.
Which of the three conditions does it fail?
The first one.
this one versus the third one.
The third one.
The first one says the function is defined at x equals c. Is it defined?
See,
Yeah.
There is a hole. There is a point there. The second one says the limit exists. Does the limit exist? Yes, it does. So the thing that it fails because? Fails to be continuous because? The limit as x approaches, in fact we can be specific here, limit as x approaches 2 is not equal to f of 2. It's that third condition that fails here. The function is defined. The limit does exist, but they're not equal to each other. This is a problem. Everybody good? All right, tell me about the second one. Limit does not exist because you have a jump discontinuity, okay? Even better, I'd want to see something like the limit as x approaches 2 of f of x does not exist because you're going to give me one of 4 reasons here. Okay, one of the options is domain restriction. Is it a domain restriction that we care about here? No. Oscillation is another reason that we say limits don't exist. We're not oscillating. Unbounded behavior is a third reason. That's not the problem. Polymono?
Limit does not exist.
Indeed, the limit does not exist. But the question on the table, my question is,
I just want to turn the camera and blink.
why? Why doesn't the limit exist, Carmen?
Don't do it. Don't do it.
The two limits from the left are not equal.
Right, limit as x approaches 2 from the left is not equal to the limit as x approaches 2 from the right. That was the piece.
He was finishing. He was doing the thing.
Oh, I'm so sorry I cut you off. Bummer. Okay, and the last one. Last one. Why does that fail? Function's not defined there, right? So f of 2 is not defined. Is everybody feeling pretty comfortable? We got this? But here's the thing though. When you are writing, when we are doing the free response section, I am going to be ruthless about this idea. I need to see the 3 steps. You're going to have to show me all 3. I am not in AP Calculus going to show you this graph and be like, is this function continuous? Everybody and their mama knows that this is not continuous, right? They're going to use the 8th grade definition. Your 8th grade definition was like, can I draw the function without picking my pencil off the paper? Right? We're not going to write that for the College Board. You're not going to be like, oh, this is not continuous. I see a hole. Hee hee hee. No. I need the 3 conditions. You're going to prove continuity like in this next example. Okay? Here we go.
Right.
So we've got one model problem. We got good timing going on here. And this is especially going to come up with piecewise functions. So for this function here, is the function continuous at x equals 1? If I gave you a graph, this would be an easy question. Everybody okay with that? Okay, I didn't give you the graph. So you're going to have to take me through the 3 steps. I need to see all 3 steps, and you have to be really careful with the notation. If this is f of x, and I want to know, is the function continuous at x equals 1? Get me started. How do we start this?
Plug it in.
Plug it in.
Plug it in. See, I lost it. I don't know what it is.
Plug in.
Plug in x where it applies.
Plug in x where it applies, okay? I want to check continuity at x equals 1, so I'm going to say, all right, f of 1. What is f of 1? Be careful here.
The bottom.
First one or the second one?
The second one.
Second one. Has to be the second one. So e to the 1 minus 1 minus 3. Yes, I need you to be able to simplify that. 1 minus 1 is going to be 0. E to the 0 is 1 minus 3, negative 2. Does that exist?
Yes.
It's a number. Good. Check. Now the question becomes, limit as x approaches 1 of f of x. Does that exist? Turn to your neighbor, have a conversation. What are you going to do? How are you going to prove that that limit exists? What would you do?
because it's not actually, you know, average.
Check this out.
So you can plug it in, right?
I'm pretty sure we have to check those.
All right.
What we just did.
I'm saying we should check the size for both of them.
It exists. It's not a.
Hey, Giselle,
Oh, God.
how are you gonna prove that the limit exists? What are you gonna do?
You have to find the limit from the left and the right.
Okay, you're gonna have to check both limits, especially because you have a piecewise function. And when we talk about limits, I'm not talking about what happens at 1, I'm talking about what
As
happens
we approach one.
as you approach. And you have to consider your approach on both sides. Thank you, David, you're like, the approach, yes. I need both, and here's where I'm gonna be ruthless. You need to know which one's your left and which one's your right. Limit as x approaches 1 from the left. I'm at the left of 1, a number like 0.9, 0.999. Palomon, which one you're going to use?
The 2 cos pi of x.
2 cosine pi of x. So I need to know what's the limit as x approaches 1 of 2 cosine pi x. For limit as x approaches 1 from the right, we've got e to the x minus 1 minus 3. You've got to make sure you're matching these up. Limit from the left, left function. Limit from the right, right function. Good news. 2 cosine pi x, if I want to evaluate that limit, just plug in.
Yeah.
It's okay. We're not trying to plug in infinity. We're not trying to divide by 0, but I need to see the work here. This is 2 times cosine of pi. Cosine of pi, you all know, is... So awkward. Cosine of pi, all 11 of you know that the answer is... -1. Excellent. Mr. Link is smiling, I bet. Okay, the limit comes out to be -1. You take the limit as x approaches 1 from the right. You're going to get e to the 1 minus 1 minus 3. Hey, guess what? -2. Your conclusion? The limit exists. Okay, therefore, limit as x approaches 1 of f of x is -2. I want to keep pushing the conclusion though. F of 1 is equal to -2. Got it. The limit as x approaches 1 of f of x is -2. Got it. Have we proven continuity?
No, last step.
No.
Stephen, why not?
Oh, we haven't looked at the. Wait.
There's 3 things, right?
Yeah.
Number 1, function is defined. Number 2,
Number 2. Wait. Oh, left and right must equal.
yes. The left and the right are equal to, and number 3,
Limit of f of x equals f of t.
right? Are these equal to each other?
Yes.
Yes.
Now, here's the thing. The thing you are likely to forget to write is that they are actually equal to each other. Most people remember to check this part. They might get a little tripped up here because of the whole like 2 sides thing. But you have to write it. I'd say something like, since f of 1 equals the limit as x approaches 1 of f of x, what's the conclusion?
F of x is continuous. Oh, just kidding, not there.
Okay, since
What's the conclusion? F of 1 and limit as x approaches 1 are equal to each other. The conclusion?
f of x is continuous at x equals 1.
F of x is continuous
At x equals 1.
at x equals 1. Do not write it is continuous. I don't know what it is. I don't want to know what it is. Don't write f of x is continuous. Right? If you stop and say f of x is continuous, what you are implying is f of x is continuous everywhere. What have you proven? You've shown that f of x is continuous at x equals 1. All that work just shows continuity at one point. Pretty okay?
Yeah.
You got to get this process down. And so you're going to need some practice. Aaron, I want you to get some practice saying it like our friends at the College Board. So can you read Essential Knowledge 1.2A2?
Polynomials, rational, power exponential, logarithmic, and trigonometric functions are continuous at all points in their domain.
Okay, so like this is like one of the things the friends at the College Board want to make sure that you know. That a polynomial is continuous everywhere. Do we know that? Okay, we know that. How about exponential functions? Exponential functions continuous everywhere? Yeah. Logarithmic?
Yeah.
The log function is continuous. Not continuous everywhere, continuous on its domain. Like when you first get past 0 and then forever, that's okay. Trig functions like the sine and the cosine, continuous. Got it. All right, so what does that really mean? The tough part is you had to show continuity at x equals 1, but if I look at this function here, 2 times cosine of pi x, is that a continuous function? This is a continuous function everywhere, but it's not defined at 1, so that's why I'm not really sure what to do. This guy over here, the exponential function, is that continuous? Also continuous. And so that means when I take this continuous function and this continuous function, because they are also continuous at the endpoints, they snap together and give you a function that's continuous everywhere. You don't need to check continuity at all the other points. You know it because of the type of function this guy is, and the type of function that this is, and how they snap together. Tonight's homework is this journal entry. It is 4 or 5 problems that are going to just get you in the habit of using this process. We're gonna look at this tomorrow when you guys come in. We'll fix up notation if we need to. Have a great day. And as I've been told, it's always a great day to be a trailblazer. It's an even better day to be a maverick.